So today we're going to do a brief introduction to differential equations. And this is probably, if you read this paragraph carefully, they just list a ton of things that use differential equations. It's probably the field in math that's used most prevalently out there. Every industry uses differential equations for something. So that's why they're so important. The idea is that you can go out into the field and you can measure the rates at which things are changing, water, electrical current, whatever it happens to be. You get your empirical data and you build a differential equation, and then the idea is that you solve that differential equation for a model that tells you something about the future. So once again, predicting the future is how people make money. And so if you can take data from nature, build a differential equation, solve it, then you can predict what's going to happen in the future. So the solution to a differential equation is a function. So a differential equation, you can think of it as an equation with derivatives, and you're going to try to find the function that satisfies that derivative equation. So anytime we solve a differential equation, we're looking for a function. And we are going to look at the simplest type of differential equation, which is first off one variable. When you get into two variable differential equations, things get way harder. Those are called partial differential equations, much more difficult than what we're going to do, which they classify as ordinary differential equations. So an ordinary differential equation has one variable. PDEs have two variables. And if you're going on in engineering, it depends on the engineering field. Usually every engineer is going to take ODEs. Sometimes ODE1 and ODE2. And sometimes ODE1, ODE2, PDE1, and maybe PDE2. So there's a lot of differential equations depending on the kind of what your focus is. My son's an applied math major right now. He's doing his first PDE class right now. So it's way harder than ODE. I never took a PDE course. So when you have more than one variable, you're talking about surfaces. So that automatically creates a much more complex situation. When we have one variable, we're just looking for a regular one variable function. Y equals f of x. It's a lot easier than looking for a surface. Z equals f of x, y. So at any rate, lots of applications for differential equations. Every engineer will use differential equations somewhere. Now, in this class, we're just going to focus on the easiest type of ODEs. When you get into your differential equations class, you'll probably go back through these two sections anyway. We're only spending a day on them. But this will give you a sense of how differential equations and antiderivatives are connected. Because there is a connection between integrating and solving a differential equation. So first thing we have to do is categorize our differential equations. And the first categorization that we're going to look at is the first order versus a higher order differential equation. So when we are looking at a differential equation, we need to identify the dependent variable. So there is the dependent variable. This is the derivative of the dependent variable right there. Right? So we're differentiating y with respect to t. The p of t and the q of t are random functions of t that do not affect the order. So these can be as complicated as you want, complicated as you can imagine. When we classify this differential equation as first order, all we want to do is look at the power that's on the derivative and the function. And so as long as the power on y and the power on dy dt, or whatever the independent variable happens to be, as long as the power is just 1 on both of those, then that is going to be it's going to be first order. So the order of the differential equation is the highest order that appears on the derivative. So this is first order because of that. This is raised to the first power, so that's going to be first order. It's linear because neither the dependent variable or the dependent variable's derivative is to a higher power than 1. And when we think of linear, we always think of power 1. And so when we talk about linear for a differential equation, the power on the y is 1, the power on the dy dt is 1. So that makes it linear. You don't have dy dt squared. You don't have square root of y. So as long as it's just y and dy dt, then we are dealing with linear. Okay? So higher order differential equations will have more complicated functions. They might have a square on the dy dt. They could have a square root on the y. They could have y times dy dt. So as long as these things are not raised to a power other than 1 and they're not commingled in any way, then it's going to be first order. Okay? And it's going to be linear. As long as these things are not commingled in any way, it's linear. And it's first order if the highest derivative is the first derivative. So it's first order because of the highest derivative. If we look at this one down here, this is going to be second order because we've gone up to a second derivative. So we've got the independent variable is t, and then the dependent variable is y, and y's derivatives. So this is a second order differential equation because the highest derivative is 2, but it's still linear. It's linear because there's no commingling of the dependent variable. Right? It's the dependent variable and its derivatives are all raised to the first power. So we don't have a y times y prime. We don't have a square root of y. We don't have y double prime squared. No weirdness. So it's linear because of that. It's second order because the highest derivative is the second derivative. So linear differential equations are going to be the easiest to solve. And then first order linear are going to be the easiest of them all. So first order linear will be the simplest. So let's take a look and first understand what the solution to a differential equation is. So this says just verify that this function right here, that's a function. We just want to verify that that in fact satisfies that differential equation. And we know what that means. That just means if we insert the y and its derivative, we should get a true statement. So nothing complicated here. We're first going to find the derivative of y. So that will be 3ct squared. And then we just plug in. So to check whether this is really a solution to this differential equation, here's the differential equation. We're just going to plug it in. So we're going to replace y prime with what it's equal to. We're going to replace y with what it's equal to. And we don't know yet whether this is true or not. That's our goal, is to figure out if that's true. So I'll put a question mark over the equals. We want to verify that that equal sign is legit. The next step is just to combine like terms and do what we normally would do. So let's just see if that simplifies properly. Sure enough, we get 0 equals 0. So therefore it checks that is in fact a solution. That's all it means to be a solution to a differential equation. All right, you all try this one. So here is the function. Here is the differential equation. So first, show that that is a solution to the differential equation. And see if, in your mind, you can sort of figure out what's going on with these two things, which we call initial values. So first start taking derivatives, plug it in, see what happens. So we start out with our function y, we take its two derivatives, and we're going to plug it into this equation here. So 27 cosine 3t. Any questions on the derivatives? Yeah?
Why would the first one not be negative? Because there's a negative 3 up there.
So the derivative of cosine is
No.
negative sign, so those two negatives offset each other. And
I knew that.
you knew it. You knew it. Okay, so then 9 times y, so we're going to have 9 times 27. Figure out that in a moment. Times cosine of 3t. Yeah?
It should be y.
Oh, did I plug in y prime?
Y double prime plugged in.
Okay, I plugged in y double prime. Oh, gosh, thank you. So it's 9 times y, so we're going back to the original function. So that's what I should be plugging in, just the original function, which we would have noticed in 1 second because it would not be 0. Okay, so then this is 27 minus 27, we get 0. So that checks. So that tells us that this function satisfies the differential equation. Now let's talk about these initial values. There's times where you have initial values and you can use your initial values to find a particular solution to a differential equation. And so let's notice that with the other differential equation, we had this constant here, right? And so we didn't have that general constant. So in typical practice, you're going to integrate to solve for those constants, and those are going to be found by using initial values. So here, the constants have already been solved for us. And so what we want to do, if they give us something like this with an initial value problem, we just want to confirm, is it true that y of 0 is negative 3? We plug in 0 for the t. Cosine of 0 is 1. 1 times negative 3 is negative 3. That's what they have. So this initial value condition is checking. Right? That's true. And then we check the y prime of 0, make sure that it's true. Here's y prime. If you plug in 0, yeah, you get 0. So this initial value problem, if we started with the differential equation and solved, we would use those to figure out these constants that are in this problem. So that constant in particular would be solved using the initial values, which we'll do in the next slide. We'll see how you do that. So all we're doing here is just verifying the derivative, the function and its derivative satisfy the equation, the initial values satisfy the two functions that they're based on.
So we don't need to verify the last two if they're already given to us?
Right. That's right.
Could you give me an example of like how you would actually use this in the real world?
Yes, if you want to make money.
Well, yeah, but like, how would you use differential equations?
So if you look,
Like a word problem.
So if you look at fish populations, that's how you would manage a fish population if you want to see. So like all of those places that manage wildlife, that manage forests, they're looking at differential equations. What's the rate of change of a population? What's the rate of change of a population if there's no predators? What's the rate of population change if you allow hunting? How many tags should you give out for elk every year? Well, it depends on what the rate of change of the population is, and they want to figure out what the equilibrium population that's good, where the animals aren't getting sick. So they're going to use a differential equation to figure out thresholds for populations. They do the same thing with money. Like if you're making investments, they're going to look at rates of change, and then that's going to inform how you invest in different.
But how do you actually do that?
Like this. You go out and you measure, like you measure the population on day 1, you measure population on day.
Okay, so you're measuring your YT function.
Yeah, so this function, you measure this. This is what you get from nature. Like
Okay.
you go out into the world, you grab your data set, and your data set has variables.
And then in real problems you're trying to find the yellow.
Yes,
But
exactly.
you get the pink and you're trying to go to the yellow?
Yes. So the pink is what you.
Okay.
So I was talking to this water engineer the other day. We were playing disc golf together, and he was talking about in their systems when they're dealing with the water for Denver and Boulder up in the mountains there. They go out. He said they have 1,000 variables. So they take those 1,000 variables and they build a massive system. And you're going to see when you get into differential equations that you can solve a differential equation with a system. It's not so important. So they take all those variables and they're plugging it into their machine and they're generating this equation. So you go out, you measure your variables, you build your differential equation, and then you want to find the function that satisfies it, because this function then tells us population is an easy one to think of. So then the population can be predicted at time t later on down the road.
Okay.
So this is the one that you start with.
Gotcha.
And so it kind of depends
So
on,
you just get that from like data, like for the population example, just like measuring the amount of species in a population and running them through like
Yeah.
a million different.
so like fish and wildlife folks, they're gonna figure out the rate of change, and they don't want the population to dwindle and go away, so they're not gonna issue 10,000 tags perhaps, because that's gonna cause the population to eventually decrease to zero. So they try to figure out that balance, like how many wolves should we have in Colorado? How many wolves is a safe population so that they don't get sick and start creating all sorts of other problems? So they figure out what that ideal population is, measure the population every year, figure that out, figure out how many
So this
wolf tags they
This
should
is
give.
just data basically. You're going from like year to year to year to year in
Yeah.
different scenarios to boil it all down to that, to find the equation.
That models the population, yeah. And that's the simplest, population is the simplest example. There's not a lot of variables. You know, there's some variables, predators and weather and things like that,
But it just allows you to take a bunch of different variables and boil them down into.
into a predictor equation.
Okay.
Like that function then predicts what's going to happen, whatever it is.
Now
So
I know
there's-
exactly what he's doing on the weekend.
Right? And they're super complicated models, like talking to this water engineer, you know, they have over 1,000 variables when they're figuring out how to manage the water for Boulder County and Denver County. And he said, and they use this technique in linear algebra, you're going to see it, called singular value decomposition. When I was in college, singular value decomposition was like this kind of interesting thing that had no practical application. When you get into linear algebra, you're going to see that you have matrices, and you can find the inverse of a matrix if the matrix is square. And singular value decomposition, when I went to school, was just like this, oh, well, you could do this thing called a pseudo-inverse. We don't have applications for it at this point. Now, there are people that all they do is pseudo-inverses and singular value decomposition to make tons of money, because normally you need, like you all know, 3 equations, you have 3 equations for 3 unknowns and you can solve them, right? So you need to have those 3 equations if you have 3 unknowns. If you have 1,000 variables, historically you would say, oh, well then I need 1,000 equations in order to isolate each of those variables. But with this SVD technique that they've developed in the last 20 years, you don't need 1,000 equations anymore. You can have less equations than you do variables, and you can do this thing called pseudo-inverse and SVD, and you can get a really good model with it. So it's streamlining how you can go out and build a functional model for what's going to happen in the future. So when you get into linear algebra, you will see SVD, and so this water engineer that I talked to, he said all they do is SVD all the time now, because they have so many variables and so few equations. They could generate more equations, but that takes time, which is money. And so now with this SVD technique, they can go out and they can create less equations, but enough equations that they can get their error to be pretty low. So super interesting.
My only thing is, how can so many like complex and like different things all be related to like one equation?
So, good question. So this function has one variable. This is the simplest type. So if you have 1,000 variables, you're talking about something you can no longer visualize. So when you have 2 variables, you visualize that as a surface. When you have 3 variables, then all of a sudden you're talking about something that's usually referred to as a hypersurface. And you've heard of hypercubes probably, and Klein bottles and things like that live in 4-dimensional space, so all we can see is a cross-section of them. And so we can't visualize it, but that's what you're going to end up with, a function that's got a bazillion variables. It's super hard. And you can think of simpler things, like if you go buy a computer, usually there's 5 specs that you're going to look at. You know, you're going to look at the RAM, you're going to look at whatever the speed of the product, 5 different variables. And you have restrictions on each of those variables that fit with the model, what you want it to do, and you make your decision based on those 5 variables. So it's that kind of thing. if you just have the 5 variables, you can imagine all the different combinations. And that's the idea, that they're going to build one function, and then that one function is going to take into consideration all 5 of those variables. But in practice, usually it's more than 5. So, and that's what linear algebra is all about. Building building systems that have unlimited variables. Whereas we're just dealing with 1. When you get into Calc 2, you deal with 2. And then you get into Calc 3, we're dealing with 1 in Calc 1. When you get into Calc 3, you deal with 2 variables. When you get into linear algebra, you deal with unlimited variables. And if you have unlimited variables, you have to use a matrix. So we can do small things in Calc 2 and Calc 3, but once you get to linear algebra, it generalizes all the stuff we do in Calc 2 and Calc 3. So, let's go to the next slide. Oh no, did we finish? Yeah, we finished. Can't tell what we're doing.
You're so passionate.
Yeah, there's too much. It's so interesting hearing what people do out in the field. Like,
Yeah.
this guy got his master's degree in aerospace from CU, and everything that came out of his mouth was interesting. You know, he was telling me about this. There's this blog, and I forget the name of it. I'll look on my phone. That he was talking about. There's a guy that does this blog. I can't remember the name. That has all these super interesting questions that he solves on this blog. And he's like, his whole office, they look at it every week and they, try to solve the problem before the guy presents the solution. Like those prisoner dilemma type things. Super, super interesting. Okay, let's get back to the boring one-dimensional case. So here we have a differential equation. It's a differential equation because there's a derivative in it. So the derivative is right there. The independent variable is t, the dependent variable is y, and there's no y in it even. So this is the simplest type of differential equation. All we do is integrate both sides. If you integrate both sides, so if we integrate the left side and the right side with respect to t, so we'll integrate. Somebody told me that if I use the back side of this, it does better. So if we integrate the left side with respect to t, and we integrate the right side with respect to t, well, we know that the integral of the derivative is the function, so we get that. And we already know how to integrate this. This is 3t minus e to the negative 2t divided by 2 plus c. So there is we would call this the general solution. So the general solution has a c in it. So that c is unknown. We can figure out what c is with some sort of initial value. They didn't give us one here, but if they gave us one, we could solve for that c. So we call this the general solution. If we had an initial value, we could get a particular solution. So when you're thinking general solution, you're thinking family of antiderivatives, right? And then some sort of initial condition would pick one of those off and give you a particular antiderivative that satisfied the initial value.
So you would go out and measure the 3 plus e to the negative 2t?
Yeah.
And basically, you're just...
So you're creating this by going out and getting data.
Okay.
And you can take all the data you get and you can plug it into a machine and it will give you the function. And then we have to solve that. That's the hard part. Machines can't always find the solution to a differential equation. That's the hard part. Like building that equation, you collect your data, you can put it into a spreadsheet and you can get that equation really easily. You can do something called regression to get that equation. If you've had stats, you know what regression is.
Is this going to be on our too?
Which part?
Just like this 9.1.
Yes, yes, yeah. Definitely. Okay, so here we have a second order differential equation because the second derivative is present, so it's second order. This is linear because the second derivative is not raised to any power, so it's linear. So second order linear. So let's just make sure that we're getting that terminology right. So it's second order because of the second derivative. It's linear because there's no multiplication of y double prime with y, no square root of y. The t function can be as complicated as you want. Question?
And are we only going to be looking at linear in Calc 2?
Yes.
Sorry.
Yeah. Yeah, you'll do some nonlinears when you get to diffie-q. When you get into diffie-q, there's very clever techniques to solve certain nonlinears.
And that's after Calc.
After Calc 3, usually. Sometimes people take diffie-q concurrently. Okay, so y prime, we're going to integrate both sides here. So if I integrate the left side, we get that. And if we do the same thing to the right-hand side, so everyone agree with that? That the first derivative is going to be the integral of the second derivative. So now let's integrate this. So when we integrate this, we add 1. We're going to get 12t cubed minus 4t. That's not how you add 1 to the exponent, though. So that's going to be a 5. And then here, add 1 to the exponent, and we get negative 2. Divide by negative 2, that's going to make that a plus 6. Plus, I'm going to subscript this because I see a second derivative. We have to integrate twice to get to y. So that means we're going to have 2 constants of integration. So any question up to that moment? Oh,
No.
that should be negative. Is that what someone was looking at? All right, so now to get to y, we integrate again. So y is going to be the integral of all of this. Y is the integral of that with respect to t. So our function y
Don't even look at
will be that. Okay, questions on that concept? Sorry.
Can we also just use different letters instead of saying C1 and C2?
Yep, you could use A, capital B, or capital C, capital D. Totally fine.
And taking and integrating the
Yeah,
the right
the left side.
the right side and the left side
Yep.
twice is not the same thing as doing a double integral, correct?
Correct.
Yep.
Yeah, so a double integral is finding the volume beneath a surface. A single integral finds the area beneath a curve. A double integral finds the volume beneath a surface. Yeah. Yeah. Believe it or not. That is true. All right, so here is one. So notice that they gave us no initial value on that first problem. So we couldn't solve for the constants. So we just had that general solution. Maybe I'll make a comment here and just call this the general solution. So this is general. General, I think that's right. General solution. So next one. Here we have, again, simplest type of differential equation. There's no y, right? We just have y prime. It's a lot easier when there's no y because then it's really just integration. So what we've seen is that ever since you started doing integration, you really are just solving the simplest type of differential equation, where dy dt or dy dx is equal to a function of the independent variable. The next section we will bump it up. All right, so let's see. I'll do this one, you guys can do the next one. All right, so we're going to integrate both sides. So y of t is going to be the integral with respect to t. So this will be negative cosine t plus sine of 2t divided by 2 plus c. So this is the general solution. And you all know how to solve for c. We're going to plug in a 0 for t. And when we plug in 0 for t, we know that we should get 4. So we're going to have 4 equals negative cosine of 0 plus sine of 0 divided by 2 plus c. So what does c equal to? What will the constant be in this case? How many? 3? So cosine of 0 is 1,
Never mind,
5. So that tells us then make sense? So that is our general solution over here. Plug in the initial value, and now we have a particular solution. So particular is when we figure out the c value and we get one solution instead of a bunch.
Do we have to rewrite the equation, or is finding the general and finding c?
Do you say that again? Do you have to rewrite what?
The equation at the end, or it's like, is finding the general solution and finding c enough?
If the question says what is the particular solution, you should rewrite it with the constant in it. Yeah, if you're trying to find the particular solution. All right, you all try this one. So second order linear, that's the type of diffie-q, so it's a second order linear. So you all try this one.
Yay, integration by parts. Just kidding. No.
Yes. Good. Integration by parts, you're right. At least once. Hopefully only once. You'll find out.
It's just once.
Once is enough?
Holy crap, that is twice.
All right, so ultraviolet voodoo on that TE to T business. TE to the T. Where's you know?
Where's who?
You know. Gone? Bad.
Did she drop or something?
No, I don't think so. Where is she? I hope she's not sick. I hope she's. Oh, and Daniel. Oh, did Daniel tell us he was going to be gone? He did anything? I can't remember if he said he was. I think he mentioned. Because he's donating some plasma, I believe.
Yeah, I feel like it's not good.
Yeah, I think he's. I think that's where he's at. Caitlin here. Aiden has abandoned us, I think. Harrison, Austin, Landon, Carter, Anna, Deepa, she's coming late.
She was literally here earlier.
Yeah, she had a meeting that she had to go to with a department, so she's off doing that meeting. She said she'd be here soon.
That's freezing up on me. Shut up.
So the problem doing it that way is that when you put t over here, you're increasing the power on t when you do the integration. So yeah, exactly. It's going to go up to t squared. So you're going to be better off putting the t in the u column. Yeah, yeah. E to t's integrals just e to the t. That's right. So let's see. So you did that. So t e to the t minus so uv, that all looks good. Yep, yeah, that's good. And then you integrate that, so plus c.
Dang.
And
Then I would need
yes, exactly. Right. So you have a C1 and a C2.
but the rest was good.
Yeah. You're cruising.
We covered this. We covered these sections in Calc 1.
Yeah.
Well,
Oh, wait.
sections.
You did 9-1? Oh, really? In Calc 1?
Yeah,
Oh. That's interesting.
or at least like part of it,
Yeah.
like a couple problems.
Okay. All right, so let's go through the derivative, the integral here. So if we integrate once, we're going to go from y double prime to y prime. So that'll be the left side integral. Usually we just write, we don't write the integral symbol again and again and again. We can just integrate left side and get to y prime. And that's going to be the integral of the right-hand side with respect to t. So it's going to look like that. And then we do our ultraviolet voodoo. So we have UdV. And you have two choices here. You have a t and an e to the t. And remember that ideally, if you have a power on t, if you put it with the u, that power is going to go down. So that's going to make the integrand simpler. If you put that t with the dv and you integrated, the power would go up, which makes it more complicated. So we're going with this. So then we're going to differentiate the left column. And integrate the right column. Then we're going to do our ultraviolet voodoo thing. So t e to the t minus the integral of e to the t dt. All right, so there is, and this is second order, so I'm going to subscript that constant. Anyone have an issue with that first integration? Make sense? So then we're going to do it. Now here you have a choice. We have our first constant here. We can solve for this c right away. It kind of depends on how the question is worded. If the question says find the general solution, we need to just leave C1 and C2 in there. If we want to get to the place where they ask us for just the general, then we shouldn't solve for this C1 yet. But we could, if it didn't, we could plug in y prime of 0 is 1 and we could solve for that C1. We'll wait till the end though. Let's just wait to the end. So then y is going to be the integral of this. And then we're going to have that product again. So we've got to integrate a second time that product. So we've already integrated t e to the t up here, so we're going to end up with t e to the t minus e to the t. That's the integral of t e to the t. And then we have to integrate this one, which is itself. And then we integrate c1. And then we get our second constant of integration. So this is our general solution. That. That's our general. Now we can use our two constants of integration, and we can figure out what those constants are. So if we see y of 0 is 0, so let's go with that one first. So y of 0 is 0. That would be 0, this would be -2, this would be 0, that would be C2. So we get C2 is equal to 2. And if we look at the derivative, so we already have that up here. So the derivative is t that, or we can just differentiate this if we want, whatever you want to do. Somehow we need to get to the derivative though. So we can go back to our derivative up there and figure out C1 from that. Maybe we should do that since we already have it. That seems easy enough. So let's go up there. So right here, let's go in green. So y prime of 0 is 1. And if we plug in 0 on the right, we get 0 minus 1 plus C1. So C1 is 2. So there's our particular solution. Make sense? So we're going to integrate twice, solve for 2 integration constants, and that's it. Question, Jose?
You just left the T for C. When you plugged in the value for C, you just left the T
Say that again.
for that very bottom equation.
Right here?
Yeah, you just.
So C1 is 2, so that C1 is going to, so the C1 comes from this first derivative, so that's going to go right there, and then the second one is also 2.
Oh, so we just leave the T alone. We just.
T is in there, T stays. Yeah, T stays. It's a function of T.
Is there homework or a worksheet?
Yeah, homework, not a worksheet. So the worksheets are always for the first chapter in our units. There's not time to do a worksheet for the second chapters. Anna?
My math lab, how does it want the scenes?
It's just going to ask you for this and this.
Okay.
Or no, it'll probably, if it's an initial value problem, it's just going to ask for that. Usually. Yeah, usually it'll just do that. All right, so let's go to the second section. Now we're going to get to a real differential equation, not just integrating. So this is the first category that we're going to see called a separable differential equation. And by separable, what this means is that we pulled all the y's into a group on one side. We pulled all the x's into a group on the other side. So y's to the left, x's to the right. And if you can separate them like that, you can integrate both sides of the equation as follows. So I'm going to first write this equation right here in differential form. So we have e to the 4t times dy dt equals 5. This equation has an independent variable of t and a dependent variable of y. And so watch how I separate this. Good grief. So to separate this, the y has to stay on the left. Because to move that dy to the right would require division, and the dy would then be in the denominator, which does not make sense for integration. So the dy is staying on the left. The dt is going to the right. We want to separate the y's and the t's. The e to the 4t needs to go with the dt so that we can integrate. So I'm going to move the exponential to the right and move the dt to the right. Now y is on the left and anything with a t is on the right. So at this stage, we've separated so that anything with the y is left, anything with the t is right. And now we do the derivative, excuse me, the integral of both sides.
Would that be divided by
Yeah.
e to the 4t?
Which makes it a negative in the top,
Oh, that's a negative, okay.
right?
How do we both?
Yeah, that's funny. So e to the negative 4t is the same as 1 over e to the 4t. But you have to have it in the numerator if you're going to integrate it. Right? We always move stuff up to the top for integration. In that.
Just like pull the 5 out.
Yeah, exactly. Yeah. So we now know really well how to integrate exponential functions. The integral of an exponential function is itself divided by the derivative of the exponent. So there is our solution. So once again, the solution to a differential equation is a function. So there it is. And that's the general solution right there. Yep.
And technically, taking the integral of both sides, each generates their own constant, but we can just move it all to one side, right?
Exactly. Yep. We think of them as combining into one. Yep. All right, see if you can do this one. So separate and solve for y for this number 11. So all the y's to one side, all the x's to the other. So the first thing you'll always do is you want to have it in the differential form, not in the prime form. And now, solve for y. Question? Jeez. Yes, y is always going to stay on the left. That's true.
But you can't, because you just flip both sides.
If you reverse both, you could do that,
That's bad.
but you can't divide by the dy. Yeah. Most people just leave the dy on the left just because it's already on the top. So, yeah, you can absolutely do that. Or sheets. Which one? Third one.
Good job, Carter. I am singing you so long.
No, you want to get work in there. Take a photo.
Oh, okay, I can just upload it later.
Yeah.
Oh, thank goodness.
Yeah. Photo up to your computer, screenshot of just the part you want, or photo of the whole thing, whatever.
That's useful.
So here, yeah, this is true, but to find the derivative of an absolute value function,
Be separate.
you've got to do. So the question is going to be the derivative first. So the derivative of this is going to be the question. So you're going to have to rewrite the natural log of this as a piecewise function. So when you write it as a piecewise function, you're going to have your restrictions. Either 1 minus x is positive or 1 minus x is negative. And then you take the derivative of each piece. And you should see something revealing about the derivative of each piece. No. Derivative of a log is no.
Well, what do you, oh, yeah.
So the derivative, so you're going to have one that's going to be log of 1 minus x and one that's going to be log of x minus 1. When you have 1 minus x being positive, the derivative is going to be the derivative of log of 1 minus x. When the inside is negative, that's going to turn it into an x minus 1.
Is it like two different, like,
Yeah, you could think of it as two different equations. You could do, you know, the break thing. You do the top piece and the bottom piece. I think you're going to notice something about that. When you take the derivative, you're going to notice something. You should. You should. Hopefully you notice something. You should notice some commonality between the two derivatives.
Yeah.
Oh, moving on here. Okay, so the dy, usually we just leave that alone on the left because it's already in the top. And so here we want the y's to the left, and we want the x's to the right. So we should end up with something that looks like that. And then to integrate, we are going to do what we always do in cases like this. And then we integrate both sides.
-2.
-2, thank you. So when we integrate this side, we get y to the -1 over -1. Integrate this side, negative x to the -1. Then we'll put the 1 constant here on the right. So this right here is a general solution. We always want to solve for y if we can. So this is general, and if it just says general solution, there's a million forms the general could take. But if you can put your general form in explicit notation, then you do it. Explicit form means solve for y. If you can isolate y, you always do it. So that's not isolated. It's general, but it's not isolated. So the first thing I'm going to do is multiply both sides by -1. And when I multiply by -1, this is a constant. A constant multiplied by -1 is still a constant. And when we're dealing with these types of antiderivative things, we can just let that c stay the same. Because we're never going backwards. We're just continuing to go forward. If we were going to plug in some initial value, it would be down here, not up here. So it's okay that these c's are different now. It's totally fine. But we still don't have y isolated. So normally what we would do, there's a couple ways you could do this. I'm going to create a fraction on the right-hand side so that it looks like this. Multiply c by x over x. Now that we have a ratio on each side, we can flip both sides. So now, therefore, y will equal x divided by 1 plus cx. So this right here is not only general, it's also explicit. So explicit is in contrast to implicit. So this is a general solution in implicit form. This is a general solution in explicit form, which is what we are always looking for if we can. So it's a general solution in explicit form. So we always solve for that y if we can. If we can isolate y, we do it. It's not always possible. Not always possible.
How do we know when it's not possible?
Because you won't be able to do it. You'll try your typical, for example. So if you have something like e to the y plus y equals 5x plus c. Can you solve that for y? No. So on the exam, I will ask you, I'll say, find the general solution in explicit form so you know that it can be done. But in practice, it'll be pretty obvious. You can't isolate y. It'll be pretty rare that, I mean, sometimes they can trick you a little bit and you can do it, but you might not see it right away. But for the most part, you can't. You'll notice it most of the time.
Why can't you isolate that?
Ooh.
Why can't you solve y for that?
Show me, how would you do it?
Log properties? Just take the log of both sides, maybe?
Oh, just take the log and that'll do it? Okay, I'm very curious. I would love to see this. So log of both sides and then what?
break the log apart, maybe?
How?
Log properties, right?
Are you trying to tell me that the square root of a plus b is the square root of a plus the square root of b?
No.
No, oh, good. Because you're not saying make this log of e to the y and log of the y.
More like log of e to the y times log of the y, right? Can't do that.
You could take log, if you have, I know what you're thinking, if you have log of a times log of b, is that what I'm saying? If you have log of a plus log of b, what does that turn into?
Log of a times b.
Log of a times b. If you have two logs that are separated by a plus, you could use a log property. But we can't take the log of a sum and break it apart. So log of a sum is indivisible, something like that. Can't do it. So there's no way we can isolate the y in that case. Yeah. But the only thing you can do is try. You try different things, and if you can't get it, then usually it's fairly obvious. You have a real question?
Yes. Oh, yeah, no, actually, no, I was trying to, no, logs. No.
Logs.
No. When you have that 1 over y
Yep.
is 1 over x plus c.
Yep.
If you put everything to the -1, could you still write it as y is equal to x plus 1 over cx? Or, I mean,
So you're saying right here,
just put everything to the -1.
so if you reciprocate, so I think you're saying this, make this y equals 1 plus x plus c to the -1?
Yeah, is that just,
That's true.
okay.
That's true. Usually we want to get rid of negative exponents.
Would you take that as an
I mean, I would take that as an answer. That's explicit.
answer? Okay.
That's explicit.
All right.
Yeah, that's explicit. It's not ideal. It's not ideal.
It's ideal because it makes me
Can't you
want
separate the bottom?
Say that again, Ari?
Theo
Can't you
Harrison.
separate that equation, or, never mind.
You got the plus. Nothing we can do here. Let's take a break. All right, let's take 10. The homework and quizzes I'm going to set to Wednesday night. I think I already said it, but just make sure everyone hears that.
My fault.
So I'll set them to next Wednesday night instead of Tuesday night. So they'll be due Wednesday night. Worksheet is due Thursday night at midnight this week. But just so you know, I am not going to lock the Thursday worksheet until the next morning. Like I'm not going to be, I'll be awake at midnight, but I'm not going to be like doing math at midnight. Well, maybe not this math. So I won't lock it until the following morning. So I come in here at 9 a.m. on Friday. So it's not going to be locked until 9 a.m. on Friday. So if you're working on a Friday night, or Thursday night, you can work into Friday morning.
This Thursday?
Yeah. Worksheets due this Thursday at midnight, meaning 9 a.m. on Friday.
So today?
Today. Oh, today. It's Thursday. Thank you. Thank you.
Yeah.
I was scared because of your shirt.
No, it's safety precautions.
Oh, safety precautions. Just to make sure.
Okay, I have not said about this.
All right. Question, Caitlin?
Yeah, I still need more help.
All right. So let's go to the next slide. Next slide. So so this says determine whether the following equations are separable. If so, solve. So I'm going to write this in the differential form first. And I want you to spend the next 60 seconds separating that. So put all your y's on the left, put all your t's on the right. So separate that, and then we'll talk about how we would get to the solution. If there is one. No. Try again. Try until you have no more umph. You forgot? You forgot where you were? I don't, but there is a box of them in the math department. If you go into the math department, right there on the left. So you go out to the end of the hall. You know where the math department entrance is?
I think.
It's the first left as you take a left in the hallway. So take a left at the hall, and then the first doors. And the box of tissues is right on the little table to the left as you walk in. I just went and got one for myself.
That's exactly right. No, it'd be.
Did anyone separate this successfully?
No, it multiplies really close, yeah.
The same base.
Did you separate it?
No, but it's not.
Can you separate it?
Times the same.
Lots.
So you have like.
Can it be separated? This cannot be separated.
So you can't.
So wait.
This cannot be separated.
Why can't you do e to the t times e to the y?
So somebody tell me what e to the t times e to the y is.
Oh, you add them. Never mind. Actually, I was lying.
Right? So this is not separate. This is what makes integration hard, is that you can't, like with derivatives, you can always take the derivative. No matter how complicated I make a function, you know all the rules for derivatives, and you can apply all those rules, and you can take a derivative. Integration's hard because you've got to do all sorts of things, and you have to sort of know when you can't do something, which is not something that happens with derivatives. So everybody agreed this is the natural way to try it, but that's not equal to e to the t times y.
What if you do?
So not separable.
It's not possible to like, what is it, an easy one or something like e negative ty over e negative ty.
So you're basically saying the same thing as this.
It is.
Like if you try to do some sort of multiplication, I think you said e to the negative t or something?
And e to the negative ty over e to the negative ty. So just like a makeshift one.
Yeah, there's still, like, if you did something like that, it's still not going to break them apart.
I feel like there's gotta be some way.
Nope.
Can you rewrite it as e to the t to the y?
You can write it as e to the t to the y. That's a good strategy. It's still not going to separate, though. Oh, why
Take
am
the
I
log of both
Why am I
sides.
looking for a regular eraser?
Natural log of both sides.
Nope. That's also a decent strategy. So, Ari, what did you say again? Okay, I remember. So if you do this, that's true, but you're still not pulling the y's to the left and the t's to the right. Right? You're still not doing that. Austin's idea, take the natural log of both sides, that's legitimate. You can do that. But now what do? If you can't, you need to have the dy and the dt out in the open. They can't be inside a function.
Well, that's when you separate it into ln dy minus ln dt.
You're talking as if you've done this before. But they're still not separated.
And dt divided by 1.
Not going to work. It's not going to work. All right, so that one is not separable. All right, try this one. This one is separable. Try number 20. Try number 20. Keep trying.
I try, okay?
Try. There is no
Partial
try.
credit, partial credit.
There is
partial
no
credit.
try. Do or do not.
I was doing until I wasn't.
Until you weren't.
You just weren't doing it correctly.
You weren't doing it correctly. But when something can't be done, it can't be done correctly.
Until it can be done. Log properties were just burned into my brain.
Log properties should be burned into your brain by now. They must be.
To the point where I try to avoid quotient rule by doing log differentiation.
Log differentiation, we're going to do a lot of it.
Oh no. In this class?
Yep. before we do any integration, we want to get all the y's on one side and all the t's on the other side.
Oh,
So yeah, you're jumping.
yeah.
Well, you're jumping. Slow down. Slow down, Tracy. Yeah, you want to separate those variables before you do integration.
How did you guys get that?
Can you teach Harrison something?
What?
He's using his method a lot.
His math. Listen, we'll do it. We'll do it. I can't remember what the answer is.
Move your paper.
Why does Harrison have a method for
Oh,
everything?
guys,
Because he's
is
that
it-
guy.
No. Let me.
He's
let
that
me-
guy.
Let me elaborate.
Oh, great.
I saw the T to the
Hold on,
street
let me
and I thought it was a
explain.
Y.
Look at what I wrote.
It's
down.
super easy to create your own method when you just rewrite things.
Okay, this has nothing to do with my method. My method actually works.
Does not.
Okay, I don't understand. It doesn't work when it's a square root. When I'm-
So did everybody get this as their separated equation?
Oh, I wrote
I thought it was a Y. I didn't send it to me. I'm dyslexic. It looked like a Y.
So that's our separation. Once we have it separated, that's when we introduce the integral symbol. So the integral symbol appears once we have it separated. And then on the left, we're going to integrate natural log absolute of y. This is going to be t to the fourth plus t plus c. So this is general, and it's implicit, not explicit. So this is general, implicit. So now we have to exponentiate both sides.
E to the Y.
So we exponentiate, we have an absolute value here. So here we have to be very careful. There's a few landmines here. Be careful.
Absolute value.
So the absolute value on the left, we cannot take it away at this moment. Absolute values are, we still don't have an explicit solution. But on the right-hand side, can't we do this? Can't we rewrite this as e to the t to the fourth plus t times e to the c? All right, that's legit. And then e to the c, that's a constant, right? E is a constant, 2.7, blah, 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 to a constant, still a constant. So we can turn that into a new c and put that c out in front as a multiplier. Now, on the left, we have absolute y, and we know that absolute y is either positive y or negative y, which is a constant times y. We can imagine dividing by that constant. Now we can take away the absolute value. These c's will be equal if absolute value of y is equal to y. These c's would be different if absolute value of y happened to be equal to negative y. But you can't take away the absolute values until you have a c over here.
Can you explain that again?
Yeah. So algebra properties here for the exponent. Do you agree with this step?
Yeah.
And then e to the c is just a constant.
Right.
So that comes out in front. Absolute value of y is a piecewise function. It's either going to be y or negative y, which is just a constant in front of y, either a plus 1 or a minus 1. And so that constant in front of y can then just sort of be absorbed into that constant on the right. And so now the absolute value can go away there. And that will be the general explicit solution. So it's general explicit.
C behaves weirdly.
C is very full, very flexible. C can float around.
Kind of like infinity.
No. Infinity is not a number. C is a number.
Whenever we make a new C, is it like a good idea to mark it as a
No.
new C? No, just.
Because we never go back.
Oh.
If somebody gave us some initial value and said, oh, y is 5 when t is 0, we plug in the 0, we plug in the 5, and we're solving for this c. If you wanted to solve for the c up here, you could, but there's no reason to go back up here ever again. Once you get down to here, if you have initial value, you plug it in here and get this c. Yeah.
But if for some reason it was a plus C, we couldn't do the absolute value trick.
Say that again. If it was plus instead of multiplication. Yes, you could not do it. Right? Everybody follow what Ari just said? This only works because we have multiplication. If this was e to the blah blah plus c out here, that's not a multiplicative constant, so we wouldn't be able to stick that plus or minus 1 into the constant. It's only because it's multiplicative here. That's the only reason it works. Squeak?
Can you look at question again? Like they give us the F. Oh, wait.
Yeah.
F.
Constant value. So that's general explicit. Now we're going to find the particular. So now we're going to find the particular. So the particular, we're told that y of 0 is 4. So we plug in 4 for y, plug in 0 for t. So that is our constant of integration. And that tells us that our explicit solution is this. So that right there is our particular. This is particular and explicit. So particular. It's particular because we plugged in a constant, plugged in that constant, so that makes it particular. It's one, not infinite number anymore, so it's one solution. And it's explicit because y is by itself on the left.
Will all the integration for diffie-q be indefinite?
It doesn't have to be. Does not have to be. Doesn't have to be.
That's creepy.
Creepy. It's like Jose's shirt. Creepy. Anyone in here grow pumpkins? Do you grow pumpkins on your farm? Or your property? Do you grow pumpkins? Big ones? How big? Oh, that's not so big. It's big enough.
Does the job. Does the job.
It does the job.
It's not American sized.
It's not big, right?
Aw, thanks
Some
for
of
that.
you go to some.
Aw, thanks
does
for
anyone
that
ever
one.
go to Anderson Farms?
Those are huge.
No one here's gone to Anderson Farms? The one that's on Highway 52, where they have the, the haunted corn maze.
Oh,
This is a problem.
So you gotta go there, right?
you know the legend of Riverdale Road, right? I doubt they're there.
Oh, I know. what you're
I
talking
never
about.
drive on
Yes,
Riverdale Road.
Oh, it's fun. It's fun.
At night?
Yeah.
You seen the blood on the sign?
You don't see like the handprints on your window?
I do.
Yeah,
That's
it's
why I
just
don't
like
go
a
there.
mist, and then
I
they
saw it
go-
once and I was like, I'm never going back to that road.
Where is Riverdale
Yeah.
Road?
You need to get the.
It's
have you
over
seen the Camaro?
northeast of
The one
here.
like the one lighted
They
Camaro?
say it's the most haunted road in
And you
America.
drive it, and then at the end of the race, if you win, you crash it.
Right? They say that there's like small ghost children floating around in blood on street signs, and yeah, you gotta be careful over there. If you haven't gone to that haunted maze at Anderson Farms, though, that is a blast. You get chased by guys with chainsaws.
You don't move
They
fast.
get mad at you if you don't move fast, and then come after you if you move too slow with a chainsaw. It's kind of fun. Yeah, my kids loved it. The first time I took them there, they were scared the crap out of it.
Didn't they like change it too? I remember last year or the year before they didn't have like a truck, and now they do. And I don't know this year, so I'm excited.
They've had. I mean, every time we've gone, you've taken the truck you've taken the truck to the back. Yeah, you're kind of in that truck with the door closed, and it's kind of creepy, and they're making you feel real freaked out. And then you get out, and you walk into the
Yeah,
deserted.
And then that's when you kind of just like.
Yeah, that's definitely worth doing if you've never done it. And then they have the paintball zombie thing where you get to shoot the zombies with the paintball guns.
Okay, that is fun.
Yeah, super fun. All right, so let's look at this one. This one you can separate. So yeah, so let's notice that this one is separable.
That's just e to the x over e to the y, right?
Right.
I haven't used it. It's only like
So because that exponent has a minus in it, you can separate it. So we are going to go y's to the left, so that's going to be e to the y dy equals e to the x dx. Very simple. But when we do our integration, it'll get a little more complex, but not much. So integral of e to the y is itself, integral of e to the x is itself. This is general, implicit.
Only 1 plus c?
I think one's enough.
So not 1 on each side?
Well, like we talked about earlier, if there's one on each side, they mash into one. The constants unite. The constants are united. So now, Austin's technique earlier, take the log of both sides, works perfectly here. This time it will work. So if we take the log of the left, we get y. Log of the right is log of the right. So we have that. So now we've got our general explicit.
Could you rewrite that as x times ln c on the right? No, never mind, you can't split that up.
Can't split it up because of the plus. Okay, so now we go with our initial value. So here's our solution to the first part. Now to get to the second part, we are told that the initial value is natural log of 3 will equal this when x is 0. So e to the 0 plus c. Now we have to solve that for c. So c is how many?
3?
No.
2.
Yes. So if we exponentiate both sides, we get that.
Oh, I forgot.
Subtract 1 and we get 2. Your technique is working less and less.
No, it's because I combined the 1 with the c.
Here are a lot of pluses.
Well, listen, I thought that you
Hold on, let him explain.
could. I forgot we weren't differentiating.
Let him mansplain it to you. All right, so that is our. So this is particular and explicit.
Square root.
I actually need to write you substitution test. Or I could just do the test without it. Yeah.
All right, anyone snagged at any piece of that?
He's gonna read your test card,
There's the part of me that really wants to prove that it can be done, but there's part of me that doesn't want to fail the test.
All right, you all tried this one then. So 26. So t times dy dt equals this product. Yes, PFD.
Well, I did this in 80 calculus. So
Oh yeah. So it's, yeah, familiar, yeah.
yeah.
Really, log properties. everyone's seen that you're going to end up with a PFD scenario. You have your y's on the left, you've got a product in the denominator, product of linear factors, so PFD, partial fraction decomp. Decomp. Good work out.
Still thinking. I goofed.
Moving. So this side is going to be partial fraction decomposition.
That's just gonna be 1 over 2 dt, right?
1 over 2 dt.
And over here it is?
So this side you can integrate right away. It's a log function. But that side you're going to have to integrate separately and use partial fraction decomposition.
So this one took it, this one took it.
Not like that. Remember with PFD, you're going to have a scenario like this. So if you're trying to integrate that,
Is that irreducible?
you're going to have A over Y plus B over Y plus 1. So that's going to be how you're going to set it up.
So if I have y plus 1, that's 1y. So then 8 plus 1.
Anyone having trouble with their PFD?
If you look at the constants in each one.
Yep. And so now you multiply both sides by that left denominator. Multiply both sides by the left denominator, and that's going to give you your PFD equation.
Right, so this is 0
Correct.
Okay.
Yeah.
We can just cancel out for me.
And then on the other side.
The y just cancel out for you.
Mhm. And that
Oh, wait, no.
is 2. Natural log. Yes. Looks plausible. Looks plausible. Yeah, let's do it up there. I can't remember the answer. Let's do the PFD first. Is anyone having trouble with PFD?
I am.
So, because this is already factored and they're both linear, whenever we do a PFD, the denominator has to be factored into linears and irreducible quadratics. These are both linear, so you put a constant on top. So these are going to be the partial fractions. And because these are linear, we can use convenient values, or we could use the traditional method, it doesn't matter. The convenient values are y equals 0 and y equals -1. If we plug in 0 across the board here, the left is 1. When we plug in 0 for y, we get a on the right here. If we plug in -1, the left-hand side is still 1. Now that's 0, so that's going to be negative b. So we'll get b is equal to -1. Is that tracking? So that tells us that this integral here can then be rewritten as dy. Let's move that dy. So we're going to have 1 over y and -1 over y plus 1. -1 over y plus 1.
Lots of ln.
Lots of ln. So both of those integrate the logs. So here we go. So we're going to integrate both sides at this stage right here. So we'll integrate. And when we integrate, we're going to have that on the left. So if we integrate that, we get natural log of y minus natural log, and I should have an absolute value around the y, and around the y plus 1. So is everybody okay up to that moment? Now we want to isolate the y if we can. So the first thing we would do is use log properties on the left to make this look like that. Then we exponentiate both sides. So exponentiate both sides. We still have this absolute value. We can't get rid of it just quite yet. This is going to be e to the ln absolute t plus c in the exponent. Can't get rid of it yet. So don't we have another one of these e to the c things? Right, this can be turned into e to the ln absolute t times e to the c.
Oh, it's just CT.
So that's going to be c times absolute value of t. Absolute value of t is either plus 1 times t or minus 1 times t, which is just a constant times t. So we can actually get rid of these absolute values right here on the right-hand side. So, work. So that we could just write as CT. Now we can get rid of the absolute value bars on the left-hand side also, because the left-hand side is also just plus or minus 1 times stuff. Plus or minus 1 times a constant is still a constant. All right. So this is general, but this is implicit, not explicit, not yet. All right, so now solve that for y. Algebra 1. Solve that for y. Make sure you can solve that for y. Yeah, that looks pretty good. So you did that, you distributed, you subtracted, you factored. Yeah, that's right, yeah. Everyone follow the process? Multiply both sides by the denominator on the left. Collect your like terms back to the left. So you're going to have y equals y plus 1 times ct, which is y times ct plus ct. Now subtract that y term back to the left. Factor out the y. Divide, and voila. Now we have what we're looking for. So this is general, but it's explicit. So whenever we can, we want to solve for y. The separation of variables. All right, next one. Unless someone has a question.
So when you were separating 1 over this, why did you do a negative?
Because in our system, down here we solve for b to be -1. So b is going to be negative 1. Oh, is this particular?
Yes.
Okay, so we've got initial value, y of 3 is 1. It was so long ago. Y of 3 is negative 1. Did I read that right?
It's just one.
Just positive 1, okay. So y of 3, positive 1. Plug in 3 for t and 1 for y. So we have 1 equals 3c over 1 minus 3c. So that gives us 1 minus 3c is equal to 3c. So that gives us 1 is equal to 6c. So c is equal to 1 over 6. So therefore, the particular solution is y equals 1/6 t divided by 1 minus 1/6 t. That's a complex fraction. We don't like complex fractions, so we're going to multiply through by a 6. And if we multiply through by a 6, that will be our simplified answer.
But you would take the 1/6 t answer?
This one?
Yeah.
You'd lose a point because that's not simplified. A fraction of a fraction is not simplified. Fraction of a fraction is a complex fraction. We have to simplify it. So we multiply top and bottom by the least common denominator, greatest common factor, greatest common factor, least common denominator.
Same thing.
It can be. All right, let's go to page 4. All right. There are times where we cannot isolate y, and we have to be content with an implicit solution. So all the ones we've had up to now, you could find an explicit solution. This one we cannot. So let's take a look at it. So first off, this will be dy dt. We always go to the differential form first. We separate, so very easy to separate in this case. So there they are separated. Integrate both sides. And that's going to give us y to the 3 over 3 minus y plus a constant, but we're going to move the constant to the other side, equals 2/3 t cubed plus the constant. So there is our general implicit solution. And we cannot solve for y here. If we factor out the y, we're going to have a y times y squared minus 1 essentially, and that's not going to be separable. We can't, separable is not the right word. That's not going to be in a form that we can isolate the y. One thing we typically would do is clear out the fractions if it's easy. Fractions are always, best avoided. And so here we can think of the c as absorbing the 3 if we multiply both sides by 3. So this would be our general implicit. So general implicit. Now we can find our particular implicit by plugging in the initial value and solving for c. So let's see if we can do that. So this says y is equal to 0 when t is 0. So we're going to have 0 on the left equals 0 plus c. So c is 0. So therefore, this is going to be our particular solution in
White.
Yeah, how did that happen? That's our particular solution in implicit form. Particular solution, implicit form. All right, you all try 36. So on the test, again, it's going to tell you whether you can do it explicitly or implicitly.
Hypothetically though, on the test, if we did do an implicit particular where we could do an explicit particular, how many points would we be done?
This one. I guess I should be careful because sometimes that conversion from implicit to explicit involves some pretty deep concepts, so it could be 2. Like that stuff with the natural log and the absolute value, that's a long process.
Right.
So it could be 2. Yeah.
Out of
5. So see if you can get your solution for this thing.
what's about the gnarliest sticky key you put on this test?
Well, this one looks pretty gnarly. It's so hard to tell though. Some of them can look way more complicated than they are. And some can look way more easy than they are. Any trouble? Multiply that out, multiply by y. That's what you gotta do. Some point, Elliot? Do you know how to FOIL?
No, I do know how to FOIL.
Or do you do some other, like?
He uses his method,
Or
remember?
you use Lloyd?
Foiling.
He uses Lloyd instead of FOIL?
Foiling is too easy to fix. U substitution is dumb.
Wow.
When
At that rate,
Stop at the end.
Work rate.
That's good. We're gonna stop here.
At that rate, passing a
Yeah.
test is dumb.
Yeah, that's good.
So I just
I
replace
still pass the
the number,
test.
By here, I just like replace.
With what grade?
Yes.
Maybe difference my point.
Yeah, that's perfect. Let's see if that's the right answer.
That is
All right, so let's go.
Okay, well, she didn't do that to me. I had an A. Actually, I actually did.
2x dx.
It was just a pity, 30 points. 30%.
So on the left side, all we have to do is multiply everything out and integrate.
It's because Levi needed A to get into school.
Casually writes Levi on the board.
Who is this Levi you speak of? All right, so at this point, once it's all separated, this is where we introduce the integration on both sides. Pretty straightforward integral because we just use the power rule. So that is general, it's implicit, but usually we want to get rid of any fractions if it's easy. So we're going to multiply through by 6, clean it up just a smidge. That constant will just absorb that multiplication by 6. And that will be our general implicit.
We should just make C absorb everything.
See, is very, it's like a black hole. Just sucks stuff up. plug in the 1 and the minus 1. So y is going to be -1 when x is 1. So the left side, we're plugging in that -1. We're going to get 1 plus 6 plus 12 equals 6 plus c. So you got c equals 13. So therefore, our particular implicit will look like this. So that's particular and it's implicit. You cannot solve that for y. I dare you to try. I dare you.
That looks painful.
Yeah, trying to solve that for y is not possible.
Log property. No.
Yeah, well. Any part of that you have a question on? Yep, quick.
Can you look at me?
Can I look at your,
Okay.
I'll
so
try.
here-
I'll try.
Are you substitution?
Okay, so implicit.
So, I got this
Whoa!
one. I got this one. So you have this.
It's just y is isolated.
Not possible. Because of this y here.
Yeah.
Implicit.
And where's your substitution? You're letting u equal this? U equals that?
So explicit is y isolated.
No. Yeah, you go this one.
This one? Okay, so 2y. So you have to divide by 2. You could use substitution here.
Yeah, so it's- I got this answer.
Use your pen. So,
Yeah.
because u equals 2 plus y squared. So du equals 2y dz. 2 equals y dy. So y dy is du. U2, so u cubed over 3. Times 2. Yeah, that works. But you still can't solve for y though, because that's y squared. Right? Do you agree? But that is true though.
I don't know when you stop. I don't know when to go first.
So if you have y to an even power, you can't take. Is everybody clear that plus or minus is not? When we say isolate y, we mean isolate y. If you do y equals plus or minus, you've not isolated y. Right? If you have y squared equals say x plus c, you cannot write an explicit solution here. When you do this, if you were to do that, this is still not an explicit solution, right? Because it's plus or minus. Right? When we say explicit, we mean you're isolating y and you're creating a single thing on the right, not a branch.
So it's better to just leave it.
So yeah, so if you have an even power on the left, you want to just leave it. Better to just leave it. Question, Ari?
Is a good rule that if there's more than 1 degree between y's, you can't separate it?
Yeah. You can't.
Or you can't?
Yeah, I know
Make
what
it
you mean.
explicit.
Yeah, most of the time, yes.
We couldn't do it because.
Okay, so let's go to our. So we don't want that. All right. Oh, question we back.
Like if it's like the square root or square the square of y minus minus 1 equal it. Let's see. We need to continue simplify, right?
Say that once again.
The square of y minus 1.
Here,
Yeah.
square.
Yeah.
So if you have this,
Yeah.
like that,
Yeah.
you would just leave that. Because you don't want plus or minus. If you take the square root, you'll get a plus or minus. We don't want to go plus. We don't want to go.
So I can keep my.
You keep your answer.
Oh.
Yeah, your answer is fine.
Oh.
Yeah, this is good.
Oh, I
You
think
keep it. That's good. That's good. If you were to FOIL this out, you would get to the up there, right? You'll get y to the 6. You'll get that up there if you FOIL it all out. You'll get it. All right, let's go to this
It's more
one.
complicated and more complicated.
I still have the right answer with even from.
So they can look different,
Yeah.
right? Just like
The
that,
graphs are the same.
just like the worksheet.
This is hard for you.
You can have answers that look different but are both valid.
Oh man.
Okay, try this one. So dy dx equals negative xy. So try to find the explicit solution to this initial value problem.
Is it really that easy? Or did I do something terribly wrong?
No, it's pretty easy.
Okay.
It's pretty fast.
This one?
Yeah, it's pretty fast. It's pretty fast.
Just cross multiply and be over with it.
Pretty fast. Cross multiply, be over with.
It was just so easy, I didn't trust it.
Yeah, this one's not too bad. I want to talk about a concept that is sort of in here, though. That is not how you integrate, though. You know, you made it easier than it is easy, but it's not that easy.
Just make sure. I feel like I'm going insane. for a second.
You made it easier than.
I feel like I'm going
It is
insane.
easy.
Is there still a negative?
Yeah.
So that was. So
Yeah,
it
yeah.
is negative x.
Yeah, negative x. The negative is there. Yeah, you're on. Yeah, that's right. You're on the right track. Well,
So how can I?
so explicit
So that's.
to this initial value.
Oh, okay.
Square root both sides. Beware.
Take the square root of negative.
Don't be square rooting a negative in this class. We'll have to take you to Anderson Farm. Stick you with the guy with the chainsaw. You're getting there. You're getting close. Getting close. Everyone's got the first part pretty clear.
Dang. Is there any way to? Is there any way to get y by itself?
We shall see.
Maybe I should use Harrison's.
All right, so we have.
You hate this at the whole class. No, I'm not doing this. This you are. It's a compliment.
It's a compliment.
Thank you.
Yes.
You get it.
It's a compliment.
Exactly.
So general implicit.
Depends on how you intend it.
General implicit. Now let's find our particular. So 0, 4. So 0 is going in for the x. 4 is going in for the y. So we get that c is 16. So then we have y squared equals negative x squared plus 16. So this says find you could do that. You could factor that. That is the worst math I've ever seen. That is like such trash. Please, please, Wait, that is like that's called there's nothing. The only way to describe that is trash. Trash.
Parker's method right there.
Trash, right?
Did you call me freaking Parker, bro?
Yeah, you can't. You know why, right?
Yeah.
Okay. Okay. Yeah. But I hope it's obvious. It's a good try.
I could teach you.
That's called the.
Don't get caught by hand.
This is called the freshman dream. So you can just separate a square root. Freshman dream.
Let's throw a 1 in front of the x while we're at it.
And in front of the C? Okay. And also, FYI, what is the square root of x squared?
Plus or minus x.
It's absolute x, right? This means the positive square root of x squared. So this has to be positive over here. This symbol means positive. So it's not just x, it's absolute.
So just put absolute values.
Put absolute values everywhere. Absolute values. Now this question says, find the explicit solution. And we're sitting here, and you're saying, wait, you've just said you can't take the square root. We can't take the square root and have a plus or minus, but notice in this context, what is the graph of this?
Upside down parabola.
No, not an upside down parabola. Think more carefully.
Line?
A line?
A circle.
Since when is
Never
a
mind,
line?
never mind. That's a circle.
A line.
I couldn't see it.
A line with x squared.
And y squared.
And a y squared. Oh,
Everybody has a method. That's Austin's method.
that, so your x parabola undoes the y parabola? They counteract each other and give you a line? Have you been watching YouTube? Okay, so this is what x squared plus y squared equals 16 looks like. Now let's look at the initial value. Where is that initial value?
So then it's
What's the initial value? Where is it on this curve? Right, so the solution to a differential equation is a curve. 0, 4. So the solution that they're looking for is this curve right here. Right? A circle has two implicit functions. Right? There's the top half is a function, the bottom half is a function. So this, can you talk a little louder? So if you are looking at a circle that's two implicit functions, this point is on the top half, so we now know that the curve that we're looking for, so remember that the initial value picks off one of the antiderivatives, you know, if we're thinking normal antiderivative land. Here there's two implicit functions, there's not an infinite number, we just want the top one. So our explicit solution is y equals the positive square root, because that's the top, of 16 minus x squared. So in this particular case, we can find a particular solution explicitly, because we know what this graph looks like and we know where the point is on it. Jose?
Is it better to leave it in the square root instead of just squaring the? Like if I took 4 minus x.
Wait!
Wait, what?
Is that the reason?
You're killing me, Small.
Wait, what?
Or is it because you can just draw it? It's incorrect.
You can't separate a square root over a plus or a minus. Only if it's multiplication.
Only if it's
Only if it's multiplication.
Oh, okay.
This is something you learned when you were an infant. You can't break apart square roots.
No, stop blaming us. Matthew's gonna be such a
Give me one
mess.
more.
It's gonna
We
be
need a third second.
So this is now explicit. So this is explicit. So whenever we have it, so when you think of, if you think about antiderivative in general, you have the plus c, which gives you an infinite family. And that initial value picks one of those away. And so this initial value right here, we actually don't have an infinite number of curves that are part of this solution. We only have two. We have the top function and the bottom function, and the 0, 4 is on the top function. Right? So like if we had a more complicated implicit curve, if we had something like this, most of the time you cannot break your implicit curve apart. Like if you see this, let me not make so many options. Let's do this. Okay. So how many functions are in this curve? Well, we have this function right here. We have this function right there. And then we've got this function here. So this curve has 3 implicit functions. There's no way that we are going to be able to find and let's just suppose that the initial value is on this one, right there. So then our solution curve is this curve, but there's no way that we are going to be able to get an explicit formula for that piece of the curve. There's no way that we can break it apart. A circle is unique because we can break apart the top and the bottom, so we can get to individual representations for each of those implicit functions. Most of the time, you cannot get to the individual representations for your implicit curve.
So just like a circle, if we had a, maybe like a,
Ellipse?
what is it called? Just a shape that can be reflectable. Forgot what it's called.
Like
Symmetrical, yeah, like you have a symmetrical shape in them. Would you be able to apart it?
and there's a gap in the middle, and it's just like a hyperbola?
No, let's say you know like an X.
Hey, we still have 5 minutes, man.
It's like an outline.
Slow down, Trixie.
Or something.
Yeah.
And you're able to like for whatever reason single it down to one quadrant.
So what Jose is saying is there are other times, like if you had a hyperbola, you could have a right half and a left half, and if your particular solution has a value that's on, say, the left half, you can separate it then, and you'd be able to get that left half isolated. Most of the time, you can't isolate the implicit curves that are part of a relation. Like it's very uncommon to be able to separate it. A circle, though, is a special case that we can do it.
And this is because you just don't know what solution set that plane is on.
Right. Like if let's go back to, let's take a look at, let's see. Let's take a look at the one Hui was talking about. This one. So let's look at that. Let's look at this one right there. So if we were to graph this right here, if we graph it, we can see where that initial value is, but do you think Desmos is going to be able to do this?
I mean, there's a 3D graph that you can use.
All right, tell me if I do something wrong here.
He just did something wrong.
Oh, I just did something wrong.
Just like Control Z it or something. I don't know.
Is that a plus there?
Yep.
And then equals.
It's plus 12y.
Okay, I will get to that. Plus 13. Oh my gosh! Why is it doing that?
Well, you're still can't do it.
And that's a 12y. All right, so there is, now where is the initial value on this? 1 comma negative 1.
Maybe this is like a learning moment.
2 or 3.
All right, so 1 comma negative 1. Let's put this point on here.
14. These things. That's like thick. Like this is like slim on low power.
All right, so everybody see that? So this, if we zoom out, this curve has 2 pieces. This curve has a top piece and a bottom piece, and that initial value is on the bottom piece. So the curve that satisfies the differential equation is that curve, but when we look at this equation, there's no way that we are going to be able to extract representations for each of these individually. There's no way that we're going to be able to find an individual representation for each of those 2 different branches, so we have to leave it implicit.
Does this come in like?
Wait, hold on, the guy with his hand up gets to talk.
Since the curve didn't have any like, what was it called, like improper corrections?
Which curve are we looking at?
Just this one.
This one.
Because remember, like the T6 over 1 minus T6, that's improper or something. Since that one doesn't have that, if we got the result that everything's divided by 6, would you accept that?
Yes. Yeah, that would be fine. That would be fine. And Harrison, what was your question or comment
in
or good
later
idea?
math is, can you find that point? Like the
That, can you get an explicit
Yes.
No.
No. Okay.
It's virtually impossible when things get not even that complicated. It's virtually impossible to figure out what those curves are individually. All right, you can pack your bag now. Oh, wait, it's already packed.
Exactly. See, look.
You guys are always looking for
Like,
shortcuts.
was a flyer.
Okay,
that's hardly true.
Yeah,
So I just wanted to.
yes, yes,
go over
yes,
this, make sure
absolutely.
there's no glare.
Yeah, absolutely. Did you follow their logic?
Yeah. Square root. I apologize for that.
Oh, no, this actually be all right.
I learned how to
Yeah,
use
this is, yeah,
Surprisingly.
yeah, and that's right. You could convert all these sines to cosines, or all these cosines to sines with the Pythagorean theorem. Hey, see you, next week, have a great weekend. So that's good. You can also graph these and show that they're different to the constant. So, hey, see you on Tuesday, have a good weekend. So that's totally fine. And here, yeah, we're just going to factor it out. That's going to be fourth, fifth, that's right. That's tangent. Secant, that. Yeah, that all looks good. That all looks good. And then that is because that power is greater than 1. This part is infinite because the power is greater than 1 and left it.
Okay, so all of this is right?
Yeah, that all looks good. Sweet, that all looks good. Nice job. Thank you. Nice job. Let me hit the pause button on this.